This lesson is called Complex Numbers 101. Let's start by asking the question, what is the mathematical symbol I? Let me give you a little bit of a history first. Mathematicians have always been interested in solving equations, and some they discovered were unsolvable, such as this one. Watch as I attempt to solve this seemingly unsolvable equation. Subtracting 1 from both sides tells me I need to find a number that when I square it, the result is -1. Well, there doesn't seem to be such a number. Clearly 1 squared doesn't equal -1. Not even -1 squared would work here, as you can see. -1 squared would be +1. And this equation seems to be unsolvable, at least in the traditional number sense. Mathematicians hundreds of years ago were unsettled by the fact that there were unsolvable equations, and in their desire to solve them, many years and discussions later, mathematicians ultimately decided that they could create a new number and call that number I. And they defined the number I to be that number which, when you square it, the result is -1. Now this seems very strange, and it was very controversial at the time. Some mathematicians, such as Gauss, Descartes, Euler, and many others, played a role in ultimately having mathematicians accept that there was this number I, that when we squared it, the result was -1. Well, what good is such a creation? Well, first of all, it enabled them to solve other equations, because this in some sense allowed us to find the square root of -1. For example, mathematicians were able to solve this equation by applying the square root property, factoring the -5, and replacing radical -1 with I. Further, mathematicians were able to solve equations like this, which they up till then were not able to, because when using the quadratic formula, which you may be familiar with, the radical had a negative number underneath it, and I ultimately played a role in finding solutions to equations like that as well. But of course, all this brings up an interesting question. What good is creating a symbol that's controversial and doesn't appear to be, in the traditional sense, a number? I mean, simply declaring that there's this number that if I square it is -1, it seems contrived, it seems fake. Well, and in some sense, it is a human creation, like all of mathematics. Nonetheless, the technology that was developed out of that is amazing. Most notably, all electronic devices that have been created over the centuries were based on the foundation that there is this number that if you square it, it's -1. And not just that one fact, but tons of theory was developed around that fact, and scientists eventually were able to exploit that theory and create amazing things. As a matter of fact, even the device that you're using to watch this video is designed on the vast theory of complex numbers that was developed over the centuries. Am I suggesting that there are imaginary numbers inside your computer, tablet, or cell phone? Absolutely not. Inside those devices is lots of wires and electricity running through those wires. What I am suggesting is that those devices couldn't have been created in the first place if there hadn't been a suitable theory or mathematical foundation upon which to design them so that they would work properly. Let's get into some of the more actual mathematics. How does I fit into the rest of math? Well, it seemed logical to mathematicians that if I was going to be a number, that we should be able to do all the normal math operations with it. For example, if I is a number, then I should be able to multiply 3 by that number. A real number times an imaginary I is often called an imaginary number. Mathematicians also decided that if we have imaginary numbers, that we should be able to add real numbers to them. And it soon became accepted that a real number added to an imaginary number would be known as a complex number. And all numbers like this, 2 plus 3i, 5 plus 1i, 6 minus radical 2i, any number like this you can imagine, that entire set of numbers is called the set of complex numbers, and here's the symbol for all those numbers. So then mathematicians grappled with the question, is a real number a complex number? For example, 7 is a real number. Is that also a complex number? Well, in some sense, no. But in some sense, yes, because if 7 is a real number, I could express it as 7 plus 0i, and then it would technically match the definition of a complex number. So in that sense, we view all the real numbers as a subset of all complex numbers. Mathematicians also decided that complex numbers should be able to be displayed graphically. Imagine the following. Think of a number line, the one you've always used in mathematics with all your familiar numbers on it, and imagine perpendicular to that, creating a new axis and calling it the imaginary axis, and putting imaginary numbers on it like 1i, 2i, and 3i. In this construct, we could take any complex number, such as 2 plus 3i, and imagine that it was corresponded to an actual point in our traditional graphing or traditional Cartesian coordinate system. And you can see that the complex number 2 plus 3i can be associated with a point directly above 2 and directly across from 3i. Now traditionally you know this as the point 2, 3. Mathematicians tend to associate complex numbers with points on a traditional graph. So while technically the point 2, 3 and the complex number 2 plus 3i are not exactly the same thing, we think of them as the same thing for mathematical purposes. So now let me introduce some vocabulary associated with complex numbers. The first vocabulary term for this number, let's by the way just for simplicity call it z. The first vocabulary term is the real part. The real part of z, denoted with this symbol, is just the real term that's part of the complex number, in this case 2. Pretty simple. The imaginary part, written this way, is the coefficient of I, which in this case is 3. It's worth noting the imaginary part is not 3i, although 3i is the imaginary number in this complex number. The imaginary part is the real coefficient of that, or 3. The third vocabulary phrase and calculation that has to be able to be made on any complex number is the modulus, which is just a fancy word for distance from the origin. In other words, how far is that dot from the origin? What is this distance here? Well, it's something that we can compute. We call that distance the modulus, but we also call it the absolute value, referring to it as a distance from the origin. So let's go ahead and find that. Call that distance d. We can find that distance by setting up a triangle and using the Pythagorean theorem. And after a little math, we now know that that distance is approximately 3.6. We tend not to put approximations for the modulus, so we'll just write it as radical 13. The last vocabulary phrase and calculation is called the argument of a complex number, which is the angle formed by the axis, the real axis, and a line going through the point, as shown here. This angle is often called the argument of z, and it's something that we can calculate. To find it, let's call it theta, and let's bring back our triangle and set up a tangent equation and use that to find theta. By the way, if this is more advanced than the math you've learned in the past, I wouldn't worry too much about it at this point in the video. But for those of you who know enough trigonometry, this should look familiar. We found that this angle is approximately 56.3 degrees. Traditionally, we tend to express the argument in radians. If you don't know what that is, I wouldn't worry about that too much now either, but we now have an approximation for the argument of z. That concludes the 4 vocabulary phrases and calculations you need to know about complex numbers, and that also completes the lesson.